Okay, so this is the second video that I'm going to upload. In the last one, I just discussed the way I will follow my lectures. So I just traced out the path on which I'm going to follow. So in this video also it will be an introductory video, where I will just discuss the basic ingredients that one needs to know to understand group action. So again, it will not be a very long video, and I will just discuss some prerequisites from group theory mainly. So the first, so I'm not going to give any motivation or something in this video. This will be just uh, say I'll start with the definition of group. It's just an empty set with a binary operation such that firstly the closure property, that if you take any two elements from that set, then say binary operation star, then this will also land inside this, and those there exist a unique element. I will call it by one. Okay. Some books write it E or something. I will just call it by one. This is the identity, such that A star of one is one star of A is a for or A, and uh, the associativity, of course, is that whether you put brackets in the first part or the second part, that really doesn't matter. Yeah, and moreover, if A star B and B star A are same for all AB, then that group is called commutative or abelian. Okay. And examples are standard examples. The set Z, the set of integers, set of natural numbers, set of reals, rational. These are all commutative groups. Of course, that is natural, and some non-commutative groups say uh, the set of 2 by 2 or set of n by n matrices over real with non-zero determinants is a non-commutative group. Sorry. Uh, okay, and the two examples that we will often use in the next video will be this Sn, that is the set of all bijection from a set of n elements. We'll call that set X, where X is the cardinality of X is. So it's the set of all bijections from uh, set of n elements to its, and under composition it can be seen that this forms a group where the identity permutation, that is the permutation that fixes all the elements, that say if I take this set as this, then uh, identity that I denoted by 1, that will take each xi to itself. That is the identity that is trivial actually to see why this is identity. And of course this is a non-permutative, because you can take two permutation and you can just take the composition from first to second and second to first, then you will get different. That's the easy thing to see. And for example, if you take the S3, the permutation of three elements, then this is this permutation that takes the element 1 to the element 2, and it takes the element 2 to 1 and it fixes 3. And similarly for 1 3, you can easily say this is 1 3 2 and this is 1 2 3. So they are not equal, of course, so this is a non-commutative group. And the next example that we'll need some and the videos later, so that is this D, the dihedral group. And one thing to clarify here actually, I will use, some book uses the notation D2n to denote the dihedral group on an in polygon, so I will use the notation D. So in our case, order of Dn, that is cardinality of this set, will be 2. And this is just the group on two generators where R is for the rotation and S is the reflection with the extra extra condition that uh, S or S inverse is R. Yeah. So, and what is this group actually means? Like you can visualize the group Sn, right? But what is this? This is just if you take say n equal to 4, then consider this square, okay, and just uh, level it, level it at 1, 2, 3, 4 in the anti-clockwise direction, and then this R is actually the rotation. So you can rotate the square in, say, to consider this rotation. So rotation is by 90 degrees. So if you rotate it 4 times, you will get back to the original. So that's because it is clear because you are rotating by 90 degrees and 4 times you will get back to the square itself that we have started. So that is the element of order 4. That is the R rotation, and there are four reflections. What are these? One is this, and observe that each reflection will have order 2 because if you reflect it once and then you can reflect again, then you will get back to the original. This is one, and this is another, and you can take the diagonal one. This is another. Take the other. This is another. So you have this four rotation, and so what will be the go? So you can go with one rotation, then two, then three, and when you do it again, you get the identity. You can take one reflection, and from this relation, you get the other one VRS, RS 4, and RS 2. And you can easily see that all these S R power I from this are reflections. Because if you fix, say this is, I'm calling this reflection by S. Okay, then if you just fix this reflection and rotate the square appropriately, you will get all the other four reflections. So this is just the S, and one of them will be SR, then SR square and SR. And you can also see that each of them is ordered 2 by just direct computation. This is ordered 2. I can compute it here, and since ASR ASR is, what is this? This is just the SR is inverse because this is of order 2. So, and this is R inverse, and now this is 1. The order of SR is 2. Yeah. So yeah, that's pretty much it from some examples that uh, we need, and from, okay, so and this group is also non-commutative. It can be easily seen. Now, okay, so coming on to the next part of, like I said in the last video, like I will start from group theory, and like I'll start from some group actions, then I'll move into representation theory for one video maybe, and then we will come back to classify some certain other group. So to start with that, the, the groups of prime order is the most easy thing to classify because I'm assuming most of them know what is Lagrange's theorem, and even if you don't, just take it on as without a proof because I'm going to give a proof anyway in the next video or in the next two videos. That is that if G is a finite group, by G I will always mean a group, so I'm not writing it here. So if it is a finite group and H is a subgroup of G, then order of H divides order of G. By subgroup, I mean just a subset of G having all those properties of a group. Yeah, and this is the notation for subgroup. Okay. Then say so if order of G is a prime. Okay. Then what happens? I can call it a lemma. Just a very easy model. Then let you take any element which is not equal to it. That can be done because prime starts with the smallest prime is 2. So you can always pick an element which is not identity. So there are at least two elements in the group. So then consider this subgroup generated by this element x. Okay. This will be a subgroup, and by Lagrange's theorem this will divide the prime p. But prime number has only two dividers, the group like the prime itself and 1. And certainly H will not be 1 because H is generated by a non-identity. So this is this. So H is a subset of G and both of them have the same number of elements. So it means this is the J is cyclic. So any prime order group can be classified using this Lagrange's theorem. And the next, uh, the upcoming videos I will try to classify the groups of order say p square, 2p, where p is odd prime. Here in this case p is odd, in this case any prime. Also the group of order pq where pq are distinct primes. And also let's say some examples classification of order to 30%. That will require semi-direct product and so I will come to that. So I guess that's it for this video. Okay, so one more thing I can say that because I've discussed about is group, subgroups and all. This is one thing that we need. I hope all of you know this. This is just say consider this. So suppose you have a subgroup of a group G. I'm not saying the finite one. In general, and consider this normalizer of H or normalizer of H inside G. That is all those elements of G such that G H G is H. But this notation is not just this. This will be a subgroup of G that can be easily seen with identities there and also associativity holds and of course the identity element of G will become the identity element of because one H one inverse. So this is a subgroup. If this becomes entire group G, then I think of this. It is equivalently G inverse is for all because this holds for every element. This is a normal. So and okay, so, and one more definition it is centralizer or normal. So what is this? This is just the quick analysis fix an element x from G and consider all those. That is all the elements in G that commutes with x. There is again a subgroup of G because one is there and associativity and those things for and yeah. So this is a central error or some people call it normal too. And then it is the center denoted by this is all the elements of G such that for all x in G. So identity is again there because it commutes with every element, and also if you take two elements, then this binary operation will also, like if you take this, it will imply AB, where AB just this is the operation of the original group is again inside center of G. Yeah. So this is one thing you can see that this is again like this because uh, you are taking for the centralizer, you are taking fixing one element of G and you are considering all those elements of G that are commuting with that particular. And in center, I am saying all those elements that commute with every. So to take the intersection of all. And yeah, so this is just the relation between the centralizer and center. Yeah, and some groups can have may have center trivial. And trivial means the center is only the identity. For example, the center of S3 is just the identity correlation. Yeah, and one result we sometimes may need during classification lemma, that is G mod Z gen also. Okay, so what is this? This is just the set of all left cosets of G inside its center. This is cyclic implies G is abelian. Yeah, and because it's a normal subgroup, you can check again. This is a normal subgroup of G. This is a notation for normal subgroup triangle. So then uh, this set of cosets, uh, say I can say it in general theory, like if H is a normal subgroup, then this set of cosets, and this forms a group under this obvious, well, yeah, this obvious rule or obvious binary operation. This forms a group, but you need that. It need not, like it has to be a normal circuit to make this definition true, because otherwise the well-definedness may get violated. Yeah. So this is a cyclic if and only, or say if this is cyclic, then it implies G must be abelian. Yeah. So that is an easy proof. I'm not doing it here. That proof is actually pretty easy. Just use the, like what you need to prove. You need to prove that take an element x and y from G, and then just you need to show that xy is yx, and that is actually pretty easy to see because you can take the coset representative of this, and this is a cyclic, so it will be generated by some a this and this, and show that because the cyclic, so this group is commutative, so just do it. It's pretty easy. And one of the things that we then need is, again I'm not going to give any proof, but if H is a subgroup of G and K is again, then HK need not be subgroup, need not be subgroup of G, although if one of H or K is normal, then HK is a subgroup, or HK is just a subgroup, not a normal subgroup. HK is just subgroup of G. And by this HK, I mean this set, right? Like all possible multiplication between elements of H and K. So you need one of them to be normal in order to establish that this itself is a just a sub. So or equivalently, if this holds, then HK is a sub. Yeah. So that's it for this video. So from the next video onward, I will start with the definition of group action. I will give some examples, discuss what are irreducible group action, then I will prove some basic results on like Lagrange's theorem, some countability results and all, and then I will move to representation theory for one video. So that's it.